Hello again. My name is Thomas Pustai. I'm a PhD student at the Vienna University of Technology, and I'm going to be your moderator for this workshop today. So welcome to the Rainbow Edge Orchestration workshop. We will start out with some welcome words by Professor Shyam Dusta. Unfortunately, he is not able to join in person, but he has recorded a short welcoming video, which I'm going to play now.
Welcome to the Rainbow Edge Orchestration workshop. I'm very happy to welcome you on behalf of the Technical University of Vienna and the whole Rainbow Consortium. As you know, platforms for managing cloud-only infrastructures such as Kubernetes or OpenStack are pretty well known. So recently, various platforms for managing the cloud edge continuum have started to emerge. Both in academia as well as industry, they have presented innovative ideas for tackling the challenges of this domain over the past years. So in this workshop, we will explore some of them and discuss them. The agenda for today's workshop is listed here. You have all seen it, I guess. So we will start with a talk of Konstantinos from UBTech in Athens, and he will provide an overview of the Rainbow Fog computing platform and all of its innovation. Followed by Thomas from Technical University in Vienna. He will present Polaris, a framework for managing and enforcing complex high-level service-level objectives. This presentation will actually be followed by a short demo where we showcase the capabilities and the developer friendliness of Polaris. Then we will have a short break. Afterwards, Deepak Vich from FutureWay Technologies in the US in Santa Clara will present the Centaurus platform for building highly scalable cloud infrastructures. And then finally, we will have a very exciting expert panel discussion on edge computing with Professor Wei-Song Shi from the Wayne State University, Professor George Palis from University of Cyprus, and Deepak Vich from FutureWay. So with that, I welcome you again very much to this workshop, and I wish you all the best for a lot of interest for attending this workshop and participating in this workshop. Thank you very much.
Okay, so let's get right started. I will hand over to my colleague, Konstantinos.
Thank you, Thomas. Let me share my screen. I hope that you can see my presentation.
Yes.
Can you see the slideshow?
Yes, yes.
All right. So I will make you an overview of the Rainbow core functionalities that has to do with fog computing, which is a fog computing platform. First of all, I'm Konstantinos Theodosiou from UBTech. I'm a software engineer and researcher. So a little recap about what fog computing is, what the Rainbow is. Rainbow is an open trusted fog computing platform that facilitates the deployment, orchestration, management of heterogeneous and secure IT services across cloud applications, utilizing different kinds of resources, such as either VMs or IoT devices, and fog device as well. So what motivates us to implement and develop this kind of platform? The motivation is that with IoT now present at our homes, work, and everywhere, the number of devices that we have around us are generating a lot of data. Thus, the amount of data expected to be in transit between IoT device and the cloud for central processing and analysis is ever increasing, putting higher demands on the cloud services, especially for real-time and mission-critical applications. What fog computing does is that it fills the gap between the edge and the data center, broadening the range of options, and as well to execute analytics algorithms, as also further reduce the amount of data that are transferred between data centers, fog devices, and IoT devices, etc. So the challenges for the platform is that the open challenge that we came up with is that we had to develop an efficient and agile orchestration of fork service and dynamic fork networks to intelligent planning, data placement, devising inter-network communication, fabric to bridge across fork and the hybrid cloud deployments, as also to effectively provide security mechanisms accounting for the distributed nature of the fork computing devices, as also the data. And of course, to take into account the energy resources and the lack of compute capabilities of the IoT and the edge devices. So our mission is to design and develop an open and trusted for computing platform to enable, by this platform, to enable the for computing to its true potential. Of course, to provide significant benefits for popular cloud platforms, for micro and distributed data management engines, and also if that is possible to extend the open source ecosystem by providing some microservices or features that the Rainbow has to the open source community. Our high-level architecture is that we're separating our architecture in four main, let's say, layers. The upper layer is the modeling layer, where we have where the end user interacts with, designs its applications, decides where to place them, onboards and deploy different policies for scalability, elasticity, or placement, considering the amount of resources that each specific component of the application needs, as also special capabilities such as GPU maybe, or special devices, cameras, or whatever else. And also is the main interaction point of the data analyst, that from where he can deploy analytics, create and deploy analytics query in order to take insights of his applications. The next level is the orchestration level, where let's say the magic happens. The first services, package of services, the backend services, where is, let's say, one of our integration points between the modeling layer, the orchestrator, logical centralized orchestrator, as also data management analytics layer. There we have some parts of, we have a service graph interpreter where we get what the end user designs, and we are investigating if we found any errors on this service graph. Where service graph, I mean application. You can think of it like a Docker Compose or a Helm chart or whatever else. Also, we have a user infrastructure manager where we can have multiple resources attached to it. So we can have multiple IoT clusters or data center clusters that are separated between each other. And of course, we have the analytics and policy interpreter, where as the service graph interpreter gets what the end user described, interpreted it, and finds if what the user provides is correct or any changes may need it. Going forward to the logical centralized orchestration is the engine that Thomas mainly have, TUW mainly has created. It's a deployment manager where it manages the deployments. The orchestration repository where we're keeping the service graph, the resource manager that manages the resources. And going forward to the orchestration lifecycle manager is the package that manages the actual deployment and orchestration of the device, of the service graph. As of the data management analytics layer is the layer that consists of two main services, the analytics service and data storage and sharing. Those two services, their work is to get monitoring data from each and every device and store them in a distributed manner, as also make analytic queries on them again in a distributed manner, gather the results and provide those results either to the logical centralized orchestration or to the modeling layer to depict them to the end user. Last but not least, the down part is the Rainbow Edge stack, where it consists from different kind of let's say them services or agents, which are helping agents for the jobs that are needing to be done in each device. Either this is an IoT device, a Raspberry, or a Jetson, or bigger devices such as a compute node. This kind of agents manages the networking stuff between the different devices, the security, as also the grab of the monitoring data, and also to talk, it manages to talk with orchestration. Last but not least, something that I would like to mention is that those kind of devices are dynamically be onboarded to each cluster. So this is also managed by this kind of agents, and of course by the mesh routing network. So a funny picture that my colleague Alexandros have made previously in other presentations, that all in all, the Rainbow is a mix of different frameworks and services. It consists from Fogify, GDNS, Trust and Security, StreamSide, Kubernetes, of course, Polaris, and a lot of stuff that maybe they didn't even come to be depicted in this image. Right now, the implementation status of Rainbow is almost finished. We're making some bug fixing and some stuff that it's last minute stuff, but in most of its part is finished. So all in all, let's say the features that are mostly need to be mentioned is that we have an orchestration protocol that manages that each device is secure and has been attested before and after have been onboarded to the cluster. We formulate cluster automatically. We provide an IPv6 overlaid Kubernetes, service graph as Kubernetes resources, and also engine as Kubernetes resources that manage the scalability, elasticity, and all those parts that TUW does, and they will explain later. Provides the monitoring and edge processing, as also analytics stuff, and of course a user-friendly, let me say, for managing the service graph and all the above mentioned things. Here are some screenshots from the platform. This is, let's say, what the end user sees, but underneath there are a lot of things that cannot be seen here. So here is the main dashboard where we can see what kind of things have been done, are running or have been done in the past. You can see the resources that have been onboarded, what kind of elasticity policies have been made, and how many active workers each elasticity policy has, where elasticity policies we mean as a low. Any possible logs that have been gathered from the backend orchestrator in order to say to the end user that something is going well or wrong. And of course, a sum up of the resources that are currently being offered and have been consumed. So in the right down hand side, you can see that, for example, right in October 21st, we had 17 CPUs have been consumed, and afterwards was 0 or 10, if I'm not mistaken. So yes, the next screenshot is how we can depict, let's say, a Helm chart or a decompose in a graphical manner. Here you can see three different services that are being connected with each other. So we have graph links, as we call them, that connect to one component and with another. This means and tells to us that to Rainbow, that a component has the need of something else. And by need, we mean that we first need to deploy this specific component, say that is up and running and healthy, and then consider to deploy the next one, or not even consider, let's say, evaluate if it is alive or not after the dependent component has been deployed. On the left side, you can see different information for each of this service. Sorry for spelling different things in different manners. So components a service. You can see what are the ports have been exposed, the IPv6 that has been exposed, and in the right side you can see live data of each service. So once you click in the service, you can see in a lively manner what are the consumed CPU usage, the RAM usage, and if you scroll down, you can see more information. Last but not least, here's a screenshot of our two main editors, the analytics editor and the SLO editor. Maybe this is a little out of date, but what you need to grab here is that the user is able to query all the available metrics that our platform offers, as also possible custom metrics that can that maybe his service has exposed. So, for example, image processing per second or something else, and make an analytics query, let's say. And by formulating this analytic query, then he can create the SLO query, where he can select what kind of action wants to make. So he may want to make a scaling out action, scaling in, actually scaling action, or scaling horizontally, scaling vertically, or migrating even his service. So these two things happen graphically. The end user doesn't need to go to write something by hand. But of course, if he likes it, he can do it by CLI. Thomas has provided also this ability. So yeah, I will not explain this. This is a sample testbed. You can see the difference of the resource that we have. Of course, here we have some VMs that cannot be depicted. But yes, of course, in the different, as also previously mentioned, you can use custom resources. So you can see that the Raspberry have cameras, and we are using the cameras for some pilots. And the device on the left side have CUDA cores, NVIDIA CUDA cores. So if the pilot or the service wants to utilize them, he of course can. So the impact that we expect to make is that to accelerate the production of successful ICT products and services for the fog paradigm, to lower the entry point for researchers and DevOps engineers to reuse and build on Rainbow platform results, and to empower innovation by making fog services more efficient and effective, by utilizing, of course, properly utilizing, of course, the provided resources. Also, we are hoping to strengthen the competitiveness of the EU cloud industry in fog and edge services, and to benefit end users and the public sector due to the adoption of decentralized edge and fog computing applications that, as we maybe all of us see, is something that emerges and is skyrocketing currently. So I hope I was on time. Of course, I'm free for any questions if you like.
Okay, thank you, Konstantinos. If there are no questions, then we can proceed to the next presentation. So let me share my screen. Okay. So can you see my presentation?
Yes, Thomas.
Okay, perfect. Thank you. So I'm going to present the Polaris framework for creating and enforcing complex service level objectives. It is used as the runtime policy enforcer and the application lifecycle manager in the Rainbow architecture, but it is also available as a standalone framework. So to get started, let's take a quick look at what SLOs are. So service level agreements, or SLAs, are quite well known from cloud computing because they define the bounds within which a service has to operate, like, for example, 99.99% uptime. An SLA consists of one or more service level objectives, or SLOs, where an SLO is a commitment to maintain a particular state of the service in a given period. That means SLOs always have to be measurable. However, today they are often limited to rather simple capacity guarantees like average CPU usage, response time, or the aforementioned uptime. But we have found out that high-level SLOs, like, for example, the overall efficiency of a service, would be much more suitable as business key performance indicators. And this is what we have realized with the Polaris framework. So let's take a brief look at the three main components of our SLOs. So on a conceptual level, we have the SLO here at the center. And then we have one or more metrics which can be read from the deployed workload or computed from the deployed workload. And these metrics go into the SLO, which periodically evaluates these metrics and then determines if the SLO is currently fulfilled or not. If it is currently violated, then it will trigger what we call an elasticity strategy. So this can be, for example, horizontal scaling. So, for example, adding new instances of a service, or vertical scaling, adding more resources to an existing service. And of course, also the other direction, or some more complex things. What we often see in production use today is very low-level metrics such as CPU and memory usage. And they go into, for example, an average CPU usage SLO, which is tightly coupled with horizontal scaling. In fact, this example resembles one of the most famous autoscalers, the Kubernetes horizontal pod autoscaler. Actually, in recent versions, HPA has received the ability to use custom metrics APIs as well as input, but this requires additional setup effort and maintenance effort. and you're actually still limited to this average operator here or a strict equality operator here. And as the name says, horizontal pod autoscaler, you are tied to horizontal scaling. So what we've tried to do in Polaris is we wanted to loosen things up a little bit. So we have removed this tight coupling here and introduced a very loose coupling to the elasticity strategy. This means that if a customer decides that they don't want to do horizontal scaling, but they want to do vertical scaling, they can easily connect the average CPU SLO to vertical scaling or some other elasticity strategy like a combination of horizontal and vertical scaling. And this also means that we can easily introduce new SLOs, like our more high-level efficiency SLO, which uses other input metrics, and it can also be connected to horizontal scaling, to vertical, or whatever. So this is one of the main innovations that we have introduced with Polaris. So what is Polaris? Polaris is a TypeScript-based framework for building and customizing all these three components: metrics, SLOs, and elasticity strategies. It is available as open source on GitHub. And one of its main goals is to have decoupling of SLOs from elasticity strategies to increase the number of possible SLO and elasticity strategy combinations. Polaris is available as a standalone framework. It is its current implementation uses Kubernetes, but it can also be ported to other orchestrators. It is, as Konstantinos already mentioned, integrated into the Rainbow platform, and it will soon be integrated into the Linux Foundation's Centaurus platform, which is led by FutureWay. And actually, you will see a presentation on Centaurus a little bit later. So let's now take a quick look at each of these three components. We'll start with the metrics. Of course, Polaris can use very simple low-level metrics such as CPU usage, but yeah, we've already seen that for high-level SLOs that might not be the best thing to do. So high-level SLOs need high-level metrics, which are not directly observable on the system. So we have come up with an abstraction called composed metric, which is an aggregation of multiple lower-level metrics. And this can be computed either internally by the SLO controller or also by an external controller and then shared through a metric store, so basically a database. And this abstraction has another advantage. You can not only compute metrics which have been observed on the system, but you can also introduce some AI predictions to predict future values of a metric. So here I'm going to show you a little example of the use of a resource efficiency composed metric. So with resource efficiency, in this case, we compute how much of our allocated resources we actually consume, and also put that in relation to the costs that our service incurs. And so the SLO controller in its control loop will get the efficiency of the target workload. For this, we have an abstraction called a metric source. This could either compute the metric directly in the SLO controller, but yeah, that would be rather inflexible. So we fetch it from the metric store. The metric store can be basically any time series database, like, for example, Prometheus. That's our default implementation. But we can also use other time series databases or even slightly different data stores, like, for example, the very flexible Rainbow distributed data storage. The metric store stores both composed and raw metrics. So how do the composed metrics get in there? The raw metrics are read from the workloads directly. The composed metrics get in there by distinct controllers. In this case, we have a resource efficiency controller, which periodically fetches the raw metrics about the workload and combines them with total cost of the workload. total cost is another composed metric. So you can see you can actually nest these composed metrics and combine them. And this is again read from the composed from the metric store. And it is written by another metrics controller, in this case, one that's implemented using KubeCost. It's a cost monitoring framework. And this writes the target workload's total cost. And that way, the resource efficiency controller can read that and compute the efficiency and then write that to the metrics store. This approach has the advantage that if we want to change the implementation of, for example, the total cost controller, we can do that very easily without affecting any of the other components. Additionally, this approach allows us to swap metrics controllers that just read the metrics from a data store and aggregate them for some predicted metrics controllers. So metrics controllers can also include AI prediction algorithms to support proactive scaling. Here, Polaris uses a polyglot approach using a small TypeScript wrapper around a prediction service written in Python. This allows the different developers of a cloud project or an edge project to focus on their strengths. So Polaris users will often be cloud developers or edge developers familiar with TypeScript, whereas AI developers are usually more proficient in Python. Once we have the metrics, we can go to the SLO controller. So the SLO controller will periodically evaluate the input metrics to check if the SLO is currently fulfilled or violated. If it is violated, it will trigger a user-configured elasticity strategy, which should correct the violation. And with Polaris, SLOs are actually easily buildable because the Polaris framework takes care of all the heavy lifting. So we have an evaluation loop that triggers automatically. We take care of triggering the configured elasticity strategy. You really only need to implement the SLO business logic. And in fact, to implement the resource efficiency SLO that I just described, you only need to write the code you can see here on the right. And we will actually take a closer look at that during the demo in a couple of minutes. Okay, the SLO then triggers an elasticity strategy. What does the elasticity strategy do? It can modify a workload's resources, its instance count, or maybe even the configuration of a workload in response to an SLO violation. Out of the box, Polaris comes with horizontal and vertical scaling. Rainbow adds another elasticity strategy that is migration to another node. And with Polaris, you can easily build your own custom elasticity strategies, either generic or specific to a certain workload. If you just want to customize the generic strategies like horizontal or vertical scaling, we also have base classes that you can simply extend. So if you want to write a custom horizontal elasticity strategy, you really only need to write these few lines of code here. Okay, now we have the SLO controller, we have the elasticity strategy controller, we have our target deployment. How do we apply the SLO to the target deployment? Because up until now, all these controllers are just sitting there and waiting. That's where the SLO mapping comes into play. The SLO mapping is a small configuration object that establishes the relationship between the SLO, the target deployment, and the elasticity strategy. The SLO mapping in the Kubernetes implementation is implemented as a custom resource definition. So it is a custom resource that we register with Kubernetes and that can then be edited and submitted like any other Kubernetes resource. And we actually make use of this concept quite a lot. So we have analogous mapping types for composed metrics and also for elasticity strategies. A quick word about type safety. Normally, when you configure your SLOs, you have to use raw JSON or raw YAML code, which has the disadvantage that you don't know if the code is actually valid before you submit it to the orchestrator. since Polaris is TypeScript based, you can actually have validation and code completion right in your editor. So we have here the service level objective and the elasticity strategy. Both define various types. So for example, the SLO defines a certain SLO configuration type as input, denoted by the yellow color, and the configuration defines a certain type of SLO target that it supports. Then the SLO also defines an SLO output. So whatever is computed by the SLO, basically the data structure that tells us if it's fulfilled or violated. And the elasticity strategy takes a certain configuration as input, and the configuration also requires an SLO output, because that's ultimately what triggers the elasticity strategy. So as you can see, the SLO output is actually the bridge between the SLO and the elasticity strategy. In Polaris, we have a generic SLO compliance output type, which we recommend to be used because this allows maximum compatibility, but you can, of course, use your own SLO output type if needed. Last but not least, Polaris is intended to be an ecosystem for SLOs, elasticity strategies, and metrics. So we have a command line interface, and we have development containers. So our CLI can be used by service providers, developers, and consumers. It will automatically set up projects and dependencies. You can generate all the Polaris CRD types, like SLO mappings, for example, and all the controllers. You get scaffolding and only need to implement your business logic. And you can use it to configure existing SLOs. What's the idea behind this? The lower the entrance barrier for new developers is, the more adopters we will hopefully have in the future. And also Polaris, the Polaris CLI is based on the very popular NX CLI, which is a monorepository manager. And this means that you can actually combine your Polaris components with other projects and components in a monorepo. And last but not least, Rainbow users can also leverage the web user interface, where Konstantinos showed you a few screenshots of, to configure existing SLOs. Okay, now the next step will be a quick demo. We're going to do some horizontal scaling of a deployment based on a resource efficiency SLO. For resource efficiency, so we compute it by taking the used resources and divide them through the allocated resources. And we actually use real-world metrics from the Google cluster dataset from 2011. These are the components of our demo. So the gray ones have already been deployed because we don't have time for everything. So the target deployment is just a Google Pause container because we're not really interested in the workload as long as we get the metrics. These metrics are exposed by a resource efficiency composed metric controller. This gets the metrics from the Google dataset and exposes them. And what we're going to write is an efficiency SLO mapping with its accompanying SLO controller and a horizontal elasticity strategy. Before we do that, are there any questions about the presentation? Okay, good. So let's move on to the demo then. So you should be able to see my terminal now. So yeah, I said we're going to scale a little demo deployment. I've deployed this in our small test cluster, and we can see it by viewing kubectl get deployment in the demo namespace. So it's called pause deployment, and we have currently one replica running. And we also have the composed metric controller already deployed. Okay, what did I do up here? to save some time, I already installed the Polaris CLI. It's a standard NPM package, so JavaScript and TypeScript users will be very familiar with this. And then I initialized a new workspace using the command Polaris CLI init and then the name of the workspace. This initialized this raw workspace, which just contains some generic configuration files, but no code. And we're actually going to create this code now. So first, take a brief look at what the Polaris CLI offers. So these are the basic commands that you have. So init we have already seen. Then we're going to make extensive use of the generate command. And then the serialize command is used for deploying an SLO mapping. And we can, of course, build our components and even build Docker images and deploy them and generate the CRDs. Okay, let's get started with the elasticity strategy. Now, of course, Polaris comes with a horizontal elasticity strategy, but just to show you how easy it is to customize it and create your own horizontal elasticity strategy, we're just going to recreate it here. So we're going to do Polaris CLI generate elasticity strategy. That's the elasticity strategy type. So the CRD. And we're going to call it my horizontal elasticity strategy. And every type has to go into a project. We're going to call this my strategies. And since the workspace is currently empty, we're going to tell the CLI to create a new library project. And since we're in the TypeScript or JavaScript world, all these libraries are actually NPM packages that can be published. So we have to give it a name. My strategies, yes. So now it's installing some extra dependencies and creating the scaffolding for our NPM library. Since this is an NPM package, you can actually reuse elasticity strategies, SLO mappings, and composed metrics easily because you can just package the definitions up in an NPM package, publish that on either on npm.js or in your private NPM registry, and that way your customers can easily make use of this code in their own controllers or in their own configurations. Okay, so we have generated the elasticity strategy, and now we're going to open up Visual Studio Code or whatever editor you prefer. Just a second. Okay. So up here, we have the libs directory and we have my strategies. So you can see all the configuration files are here, which define the project and which are needed for publishing this to NPM. And then here we have the elasticity strategy. Let me just quickly zoom in a little bit so you can see this better. Okay. So here, the CLI has actually generated a to-do list that we can follow in order to complete our elasticity strategy. But yeah, so I'm just going to walk you through this. We're not going to do every single step here. I'm just going to quickly walk through this. So on top here, we have an interface that defines the elasticity strategy configuration. This is the user configuration for the elasticity strategy, because the main input for the elasticity strategy is actually the SLO compliance or the SLO output. We can define that down here if it takes SLO compliance or some other SLO output as its main input. And this is just additional configuration for the user. So since this is a horizontal elasticity strategy, we're going to allow the user to configure the minimum and maximum replicas. I'm just going to paste this in here to save time. And down here, we have what we call elasticity strategy kind. This defines the type of elasticity strategy. So first of all, it's going to be used to create the Kubernetes custom resource definition type. There you need a domain to identify it and let's say class name. This is all defined in this elasticity strategy kind. And also, as I already mentioned, the elasticity strategy kind specifies what type of SLO output this elasticity strategy requires, and also on what SLO targets it can work. And then this down here doesn't need to be modified at all. It's just for generating the CRD. Okay, we don't need to modify anything here because we're fine with the default selection. So we're just gonna generate the CRDs now. So we do that with Polaris CLI gen CRDs, my strategies, the project name. It's going to take about 20 seconds or so. Okay. And we can, actually, let's take a brief look at it so that you can see that I'm not cheating. So in the CRDs directory now, you can see you have a standard Kubernetes custom resource definition that describes all the details about the elasticity strategy. And actually, Polaris is the first project to allow generating CRDs based on TypeScript code, because usually you would be using Cube Builder and Go data structures to generate your CRDs. We're the first ones to have done this in TypeScript. And we're gonna now apply this to our cluster. Okay, and it has been created. So far, so good. We have the elasticity strategy type. Now we need a controller for it. So Polaris CLI generate elasticity strategy controller. Gotta make sure I don't mistype. No, it's fine. And we're gonna call this my horizontal elasticity strategy controller. And each elasticity strategy controller is, of course, responsible for a certain elasticity strategy type. Of course, this one is responsible for the one we just created. So it's in, so we need to specify the package, elasticity strategy type package. That's my org / my strategies. And then we have estrat type. And here we can just copy that, my horizontal elasticity strategy. Again, generator is starting. And so we have some scaffolding already generated, and we need some additional dependencies that are being installed right now. Okay. So controller has been generated, and let's take a look at it. So that has been added here in the apps directory. As you can see, we have all the configuration files again needed for building this. We also get a Docker file, which we can use to build a container image. We get the Kubernetes deployment manifest files. So everything ready and generated. We have all the startup code here. So here in the main TS, we load the Kubernetes configuration, we initialize the Polaris runtime, and we initialize what we call the elasticity strategy manager, which watches the cluster for new elasticity strategy configuration objects. That's all, nothing that the developer needs to worry about because it's all being taken care of. We only need to implement the elasticity strategy itself. Again, we get a to-do list that we can follow or not. In general, an elasticity strategy controller that is generated is a generic elasticity strategy controller. So it contains an execute method, which will run when the strategy needs to be applied to a workload in response to an SLO violation. And it comes with what we call a stabilization window tracker. So by stabilization window, we mean the time phase between two executions of the elasticity strategy. For example, if you need to, if the SLO is violated and you need to scale out, then usually you want to wait some time before applying the elasticity strategy again to avoid some ping pong effects. And that's what the stabilization window tracker is used for. So we, so we support all that. And we can actually make it even simpler since we want just a horizontal elasticity strategy. And as I mentioned, we have a base class for that. And today we also have some already written code to make things even faster. So if we just want to write the horizontal elasticity strategy, we can extend the horizontal elasticity strategy controller base class. And there is an analogous class for a vertical elasticity strategy. And for the horizontal one, we just need to compute the new scale, so the new replica number based on based on the input that we get. So we have done that here. And the next step is to build the horizontal elasticity strategy controller. We have the docker build command in the CLI. And I'm going to copy this here. So it's Polaris CLI docker build project name. And this will fire up the build process. Don't worry, you don't have to watch the whole thing. I'm just going to cut it short because I've already pre-built the images yesterday, and we can just deploy the ready-made images. So for deploying, we have the Polaris CLI deploy command, and this will use kubectl in the background, so it uses the default cluster that's configured in your local kube config. And as you can see, it creates all the necessary role-based access control objects and the deployment as well. And let's see if it actually worked. We have the Polaris namespace, get deployments. And down here you can see my horizontal elasticity strategy controller, 17 seconds. So that's what we have just deployed. Okay. Elasticity strategy done. Next part is the SLO controller. So actually, no, not the SLO controller, the SLO mapping type. We can't create a controller without having a type that defines the SLO. So we use Polaris CLI generate SLO mapping type. And we're going to call this efficiency. And again, we need a project called my SLOs. This is also a new project. So create lib project equals true. And we're going to give it an import path, my org / my SLOs. Okay. So it has been generated. And let's see, here we have a new project, my SLOs. And in here, we have an SLO mapping. Again, we have a to-do list, and the structure is quite similar to that of the definition of the elasticity strategy. So we have an interface for the SLO configuration. The big difference to the elasticity strategy is this is the main configuration for the SLO, because an elasticity strategy gets its most important input from the SLO output, but the SLO controller, of course, gets the most important input from the user, because we need to know what our goals for the SLO are. And so our goals will just be the target efficiency, and that's a number, and the efficiency of the target in the range between 0 and 100. Actually, you can define constraints on these CRDs. So you can write at minimum 0, at maximum 100. And these will actually then be included in your CRD definition. Don't write min-max, it's minimum and maximum. In fact, I just checked it in my cheat sheet because I always mess this up. Yeah, once we have the configuration, we have a type for the SLO mapping spec. So spec in Kubernetes is basically the payload of the object that describes what it should look like. We have in the generic type parameters, we have the SLO config up here. And then we define the output type of the SLO. So by default, it's SLO compliance. But we could, of course, also change this to something else if we wanted to. But here, SLO compliance is fine. Actually, I'm gonna show you what SLO compliance looks like. So it has one important property, the current SLO compliance percentage. If it is 100, then we're all fine. The SLO is perfectly fulfilled. If it is above 100, then it means we are underperforming, so we need to execute an elasticity strategy to either scale out or scale up or something similar. If it is below 100, we're actually outperforming the SLO. We're much better than we should be, and we're probably wasting money right now. So we should scale down or scale in or something similar. You can also configure a tolerance value, but yeah, let's forget about this right now. It's just a detail. Then you can configure in your SLO mapping spec the SLO target as input. So here we support basically any target because SLO target is the most generic one, but you could also restrict this. For example, if an SLO is only applicable to, let's say, a REST service, then you could create an abstraction for that. Or if it's only applicable to a SQL database, you could create an abstraction for that and use that here. Then the SLO mapping class down here is used for the CRD generation. We could change the group here if we wanted to, but we're fine with the default one. So just make sure the file is saved. And then it's again time to generate the CRDs. Project is called MySLOs. And it has been generated. Let's take a brief look. Here we are. And let's try to find the target efficiency. Yeah, right, here we are, target efficiency. So you can see it has copied the description, and it has also created the constraints here, the minimum, maximum. Let's register the CRD kubectl apply -f and the whole directory. And we have created the efficiency SLO mapping CRD. Okay, so let's now generate a controller. SLO controller. We're going to call this efficiency SLO controller. And so analogous to the elasticity strategy controller, the SLO controller has to be responsible for a certain SLO mapping type. So we specified a package of that type, which is my.org/my_SLOs, and the SLO mapping type is efficiency SLO mapping. And generator is spinning up. Again, some further dependencies that we need. Shouldn't take too long. So actually in this SLO, remember that I mentioned in the presentation that the composed metric controller has already been pre-deployed. So we are actually going to reuse a composed metric type that has been defined in another NPM package. So we're going to install this now, this NPM package. So Polaris slok/efficiency demo. And this is the mechanism that I mentioned before that you can use to share type definitions with your customers so that they can reuse things in their own projects when configuring their deployments. Okay, so it has been installed. And then let's see what we have generated. Efficiency SLO controller. Again, all the configuration, Docker file, manifests already. In the main TS file, we have a similar initialization like for the elasticity strategy controller. We load the kubeconfig, we initialize the Polaris runtime. We get some additional environment variables in case we want to read something from Prometheus, which in our case, the composed metric abstraction will do. We automatically initialize the SLO mappings library. That's where we defined the SLO. So this is my.org/my_SLOs, efficiency SLO. Then we start the control loop. The watch manager that will watch for new elasticity, sorry, not elasticity, but SLO mapping mappings in the cluster and trigger the control loop for each SLO mapping. Here we have a small to-do. If we're using additional libraries, like we are doing in this case, we need to initialize them. So we are using the efficiency demo library. So we need to initialize this here. Why do we need to do this? Remember during the presentation, I said that Polaris is actually orchestrator independent. So we have a transformation service that takes objects, that takes orchestrator independent Polaris objects and transforms them to Kubernetes objects. And inside these init Polaris lib functions, we actually register all the types in that library with the transformation service. So that's just a little background info. And next, we can go to the SLO controller. So if previously in the SLO mapping type, if we had changed the SLO output type to something else, we would need to change this here as well. But we stuck with SLO compliance. That way we are most compatible. So we are fine. We have two methods. The configure method, which is called whenever a new SLO mapping is found in the cluster or when an SLO mapping is changed. and the evaluate method, which is called periodically by by the control loop. And yeah, as you know by now, I have prepared the code, so we're just going to paste it here. So what are we doing in the configure? We just store our SLO mapping, and then we configure the composed metric source for getting the efficiency metric. What does this do? This will create an efficiency metric mapping in our cluster, which will trigger the efficiency metrics controller and tell it to compute metrics for our target workload. In the evaluate method, we just call our helper method, calculate SLO compliance, and then return the result. Calculate SLO compliance, since we're using a composed metric source, is very, very simple. We just obtain the current value of the composed metric through a promise, and then once we have that, we divide the target efficiency by by the actual efficiency, and that is our SLO compliance. Okay, again, we can build this using the Polaris CLI efficiency SLO controller. Docker is starting, downloading everything, and we're just going to cut it short again and deploy the ready-made image. Deploy efficiency SLO controller. Okay, let's see if it's there. Yes, it is. Efficiency SLO controller here. Perfect. Okay, we have the SLO controller. We're basically now at this stage here. We have everything deployed. Now we need to configure our SLO mapping. To do that, we can, of course, use the CLI. So we generate an SLO mapping, call that demo efficiency. And of course, it has to conform to some SLO mapping type. So we give it the package name and the name of the SLO mapping type. So that is efficiency SLO mapping. Okay, has been generated. We now have a new folder here, SLO mappings. We get a README file that explains us how we can apply these SLO mappings to our cluster. And we have the efficiency SLO mapping instantiation here. So we just instantiate the class and export this as the default export in the file. And this will be picked up by the CLI and can be used to generate everything that's necessary to apply this in Kubernetes. So let's configure it very quickly. Namespace is demo. That's the name of the SLO demo efficiency. And the target is a Kubernetes deployment. So the group is apps version v1, kind is deployment, and the name is pause deployment. Two to-dos, change the elasticity strategy if needed. This is the default horizontal elasticity strategy, but we want to take our own. So we take this one, new my horizontal elasticity strategy kind. Let's see if VS Code can be. No, let's just write this here. My horizontal elasticity strategy kind from my org strategies. Did I misspell something? Why doesn't it find it? That's always very... no, it's not called elasticity strategy king. It's elasticity strategy kind, of course. Yep. Okay. So next thing, we need to specify the SLO config. And since we are in TypeScript here, we can use code completion to tell us what we need to write. So target efficiency, we want that to be 90%. And then we also want to configure the stabilization window, because remember, the stabilization window would prevent these ping pong effects by scaling too often. But actually here, we want to see something very quickly. So we reduce the stabilization window to 10 seconds. And then we supply some additional configuration. We want this to use 10 replicas at most. Okay, we have saved it. And now we serialize this demo efficiency and pipe it directly into kubectl apply. Okay, has been created. Now on the second terminal, we are going to watch our deployment in the demo namespace. So we have one instance at the moment. And we're going to follow our logs of the efficiency SLO controller. You can see it has picked up the SLO. Currently, everything is perfectly fine. But we have, of course, selected a portion of the Google dataset, which will cause it to scale very soon. So the composed metric controller is replaying this segment over and over. So right now, we can see that we are outperforming the SLO because of very low SLO compliance percentage. But yeah, we can't scale in even more because we are already at 1 replica. But we should arrive at a scale out point very, very soon. Hopefully. Every time I tried it, it worked. Yes, here we are. So SLO compliance percentage 635. So either we have a denial of service attack that's currently coming, or a very high load. And as you can see, we have scaled out to 7 replicas. Okay, and yeah, with that, the demo is complete. Thank you very much for your attention. Do you have any questions? Okay, so the schedule, we now have a short break of 10 minutes. So yeah, let's take this break, and we will resume at 7 p.m. Central European Summertime with Deepak Vich's presentation on the Centaurus platform.